Good morning, and welcome to this Android accelerated rendering session. Yes, Chet worked really hard on that sound effect once again. I believe, yeah, if you want to tweet because you were boring, you have hashtags at the bottom of the slide that you can use so we can see what you were saying about us later. If you have feedback, there's this incredibly hard to parse link. So go there, tell us what you think about the presentation. And for those of you who don't know me, I'm Romain. I've been working on the Android UI Toolkit team for about 4 years now. And on Android 3.0, I was in charge of designing and implementing the OpenGL pipeline that we're going to talk about in this presentation. And joining me today is Chet Haase, who's been working on animation and was helping me on the pipeline as well.
Oh, I thought I was going to do this in mime. OK, so contrary to popular belief, we've actually been doing GPU stuff for a long time. People keep asking us for GPU support for the platform. We've actually got it all over the place. It just may not be quite obvious to you. For one thing, most of the games are being written using the GPU, either using the NDK, OpenGL ES1, or OpenGL ES2 are both supported for the NDK. Or they could be using the SDK APIs, which are basically wrappers around those same libraries. We also use it for window compositing. So we do software rasterization of everything, all the graphics that we draw, and that gets drawn into a buffer that is then composited by the hardware. So there's lots of GPU stuff happening already. Oh, including live wallpapers, which were written with an earlier version of RenderScript, which uses the GPU. So there's all kinds of stuff that's actually using the GPU. However, the basic UI is not using it. So everything that we draw on the screen in the framework, when you say canvas.draw a line or canvas.draw a rect or any of these shape operations, all of the stuff that the standard views are using, that goes through our Canvas APIs. None of that stuff is accelerated, right? And on top of that, the entire UI that you're using and all the apps that ship with the core platform are not accelerated. And that's kind of what people mean is, when is that stuff going to get faster? But do we really need it? Because all the CPUs are getting faster. The tablets are coming out with multi-cores. I mean, there's lots of devices that are coming out with faster CPUs, more, bigger, better, lots of memory to use, multi-core. So do we actually need this thing accelerated? Because maybe we can just depend upon the hardware that we're getting to speed it up for us.
And one of the key differences between tablets and phones is that now we have much more pixels on screen. And the difference is pretty staggering, actually, between a Nexus S that has a high-density display and the Motorola Zoom tablet that you see here, or the Samsung tablet that you got yesterday. I think we have more than 2 times the amount of pixels on the tablet. And now it's 2011, and you're expecting richer experiences. You want more animations everywhere. You want smoother animations. And just in general, you want the UI to be perfectly smooth and nice to use. So here's the problem that we've run into. This is a little graphic that shows you the expansion of the number of pixels since the G1 that shipped in 2008 up until the Motorola Zoom that shipped a couple months ago. And that's the red line. So you can see that between the Nexus S and the Zoom, we've seen a dramatic increase in the number of pixels. And the yellow line shows you the available bandwidth that we have to move pixels around between the CPU and the memory. And unfortunately, the bandwidth itself has always been on par with the number of pixels, so it was good enough. But now we have more pixels than we can afford to move on the bus. So software rendering is not enough. So with Honeycomb, we've introduced a new rendering pipeline for the UI. So all the standard drawing operations that Chet mentioned on the canvas, for instance, draw a line, draw a bitmap, draw text, are now hardware accelerated if you opt in. And to give you an idea of the level of compatibility that we have, all the standard applications running on Android 3.0 are running with this new pipeline. So the browser, this includes the web view, Gmail, contacts, books, they all run with hardware acceleration turned on.
The acronym that we have here, we're trying to popularize. It's actually pronounced GAPUI. So it's user interface on the GPU. That's the whole idea.
I'm sure it will have a lot of success.
You can start using that today. So it helps to understand how the rendering model used to work and then how it works now under this wonderful new world of GPU acceleration. So in the releases prior to 3.0, a view would be redrawn. So let's say a button is being drawn, and so its onDraw method gets called. And then it calls rendering operations. It calls these drawing operations on the Canvas API. It's going to draw a border. It's going to draw a background, gradient fill, or a bitmap. It's going to draw some text, whatever. And then we go into the software rasterizer. We happen to use a library internally called Skia, and that basically turns these operations into pixels in the frame buffer. So it does a little Bresenham algorithm or whatever it does and actually lights up the pixels in the appropriate color. And then it gets copied onto the display. So all of that's very straightforward. In the new model, we have this alternative way of doing it instead. So we go through the same process from the view's perspective. Nothing changes there. The button's onDraw method will get called. It'll issue the rendering calls into the Canvas API. But instead of going through the software rasterization route, we go through an alternative path that turns those into GPU operations, essentially calls into OpenGL. So instead of walking the line and casting out pixels, we say, hey, OpenGL, why don't you draw a line for us? And this is basically the pattern of all the operations, all the GPU acceleration stuff that we do. And there's different ways of doing that that Romain is about to talk about. But basically, everything becomes a series of operations that we send down to the GPU via the OpenGL ES2 library.
So with OpenGL, the only primitives we have available are points, lines, triangles, and textures. I mean, it's a simplification of OpenGL, but that's pretty much what we have to work with. So we wanted to show you, we wanted to give you a peek behind the scenes, like what happens when we draw some of the standard elements, UI elements on Android. So this is a simple list view running on Android 3.0. And that list is turned into a combination of those points, lines, triangles, and textures that I just mentioned. So for instance, that list view, once it goes through the OpenGL pipeline, looks like this. This is a screenshot I took using one of our debugging tools that shows us what exactly is used by the GPU. So you can see the mesh that we're using to draw all the icons, the pieces of text. And at the top and bottom of the list, you can see these really wide rectangles. Those are for the fade regions that you see at the top and bottom of lists when you scroll them.
I actually like this version better. I think it's very geeky cool. You can't read the text very well, but it looks really neat.
It's a new style of UI. Here's an example of a button. So we will ignore the text in the GPU transformation, but a button uses something we call 9 patches. So 9 patches are pretty much textures that we stretch in very specific ways. And it's made very easy by OpenGL because we can just map that texture onto a mesh that looks like this, and OpenGL will do the work for us of stretching the texture correctly. The text itself is drawn in a very similar way to path. So here we have this beautiful blue line with curves. And to render a path like that, what we do is we generate an alpha texture, so it's a mask. And we apply this mask on a very simple piece of geometry, a quad. So we have only 2 triangles. And then with our fragment shaders, we colorize the path. So this is what it looks like. This is our mask. This is the content of the OpenGL texture. And we just draw it on top of this simple piece of geometry. And text is drawn exactly the same way. Our text, this is a very common way of drawing text in GL. You have this mask that contains your font, and you just apply it on very simple pieces of geometry. For those of you geeks who love OpenGL and have used OpenGL before, I just wanted to show you a couple of the shaders that are generated by the renderer. And if you don't know anything about OpenGL, you probably don't care about those next 2 slides, so we won't go into the details. But one of the difficulties of implementing the OpenGL renderer was we have so many different combinations in our API that we could not write all the shaders by hand. So we have a program that generates the shaders at runtime, and I think we have like several millions of combinations of shaders possible. So this is an example. If you draw a piece of text and you colorize the inside of the text with a gradient, this is the vertex shader that's generated by the system. And the vertex shader, for those of you who don't know that, is applied to every single vertex inside a mesh. So with a triangle, you have 3 vertices, and each vertex runs this code. This is the fragment shader. Again, just an example, you can see that we have two textures. Let me show you. Two textures right here. So that's the texture that contains the font, and that's the texture that contains the gradient, and the shader simply combines them into something that looks awesome.
So obviously this is really complicated stuff, and we did a lot of work to make this work, and there's all these really gnarly meshes being sent down with texture maps and complicated shaders. So then the question is, how do you actually access it? What is the complicated API that you need to be aware of to enable hardware acceleration in your applications? So first of all, no, actually that's it. Basically, opt-in. The only trick is that you need to choose to have hardware acceleration for your application, because as we'll get into a little bit later, there may be some stuff that doesn't work quite correctly for you. You may be using capabilities of the Canvas API that we simply haven't enabled on the GPU at this time. So you need to test your application, make sure it works for you, and then go ahead and opt in at the application level by issuing this in your manifest file. There's a little bit more detail to it than that, which is that you can enable it at the application level or at the activity level or at the window level. You can also disable it at either the activity or the application level. And then finally, if your overall application is running with hardware acceleration enabled, you can disable it for particular views if you need to. You can't enable it per view, but once the application has it running, then you can disable it per view. And this turns out to be useful for particular situations where you really want to use GPU acceleration, but your custom view clips against a path, which is not currently supported. Well, what you can do is just have that single view use software rasterization. Everything else in your application is happily using the GPU. So here's a little bit more detail about how to actually opt into this stuff. So at the application level, as I said, you can opt in, say hardware accelerated equals true. Maybe there's a particular activity that can't use it for some reason, so you can disable it at the activity level. By setting the same flag equal to false. You can actually see this in the SDK API demos. There are some API demos that used Canvas APIs that were not accelerated at the time that they were written, so the activities opt out by setting this flag to false, even though the overall application is hardware accelerated. And you can also opt in at runtime on a window level by setting this flag, the flag hardware accelerated flag. And finally, you can disable it at the view level by using a software layer. We're going to learn more about layers in a few minutes. There's more to it than simply being able to disable hardware acceleration for a view. But basically, if you want to draw your view into a bitmap, you can do this, and that will use software rasterization.
And if you plan on using hardware acceleration, you might run into several issues where you are using an API that's not currently supported by the pipeline. So you might want to use one of those two methods to check whether hardware acceleration is currently enabled. For instance, the team working on the launcher application for Android 3.0, they want the code to still be able to run on our phones that don't have hardware acceleration at this time. So their code contains some of these checks to perform some operations in one situation and some other operations in the other case. So for instance, if the hardware acceleration is on at the view level, you might want to display fancier graphics or enable more animations. But what's very important is to check the hardware acceleration at the canvas level, because even if your application is hardware accelerated, the canvas that's passed to your view for drawing might be a software canvas. If the view for some reason is rendered into a bitmap, then the view will be rendered in software. So just remember those two methods. You should not have to use them in many situations. I haven't used them myself in any place, I think, so far, but it can be very useful. And like we mentioned, we do not cover 100% of the existing 2D API with the hardware pipeline. And there are various reasons for that. We had time constraints. There are some APIs that are very rarely used, if at all, by applications. And there are also some of the APIs that we have on the canvas are difficult to implement efficiently on the GPU. So we had to make a decision, and some of these APIs were left out. There are not that many, though.
Yeah, it's important to point out that before you get too worried about all the stuff that we don't support on the GPU, everything you see on the tablets that you got yesterday is hardware accelerated. In the home screen, the launcher, the all apps view, everything in the basic UI, also everything in the applications we ship. So that's the level of support that we have for graphics acceleration. Everything you're seeing in contacts and Gmail and YouTube, and all the API, all the UIs for all these applications in the home screen itself, that's all supportable by the GPU. These are more like corner cases that you should be aware of, but won't run into with the standard views, and probably won't run into with your custom views either.
Yeah, if you use the standard views and the standard drawables, you'll be fine. So this is the complete list of APIs we do not support in Android 3.0 and I believe 3.1. When you clip, you can only clip with rectangles. Clipping with path and regions is not currently supported. Drawing pictures is not supported, although this should be pretty easy to add in the future. Draw points was added either in 3.1 or ICS, I don't remember exactly, but it's coming. The draw post text and text on path are currently not supported, but we probably will. There's no technical reason why we wouldn't. Draw vertices, same thing, we can support it, we just didn't have the time to do it. And on the paint, you can't set a mask filter or rasterizer. And I don't even remember what the rasterizer does. So it's probably not very useful.
Yeah, I think it rasterizes.
I'm sure it does. On top of that, some of the supported APIs have limitations. So if you clip with a rectangle and you have a 3D transformation on the canvas, the 3D transform will not be applied to the clip rect. And there are some operations that you can do on the clip rect. You can do an XOR, a difference, or a reverse difference. Those are currently not supported, and I've never seen an application use them. Draw bitmap mesh, we ignore the colors array at this time. Again, we can support it. Draw lines, we don't have anti-aliasing, although ICS will add support for that.
I hope so, or else I've been wasting my life for the last 3 weeks.
That was part of my plan. Set draw filter, we completely ignore it. And on the paint, if you try to use to enable dithering or to disable filtering on bitmaps, we ignore that. Those flags are here to lower the quality of the rendering, which makes sense in software because you want to save memory and you want to save CPU time. On the GPU, we have enough horsepower that we can always choose the high quality version. And finally, shadows work only on text at the moment. And finally, there's this thing called the Compost Shader. How many of you have ever used a shader on Android? Yeah, that's not many. In a way, that's good, but the other,
I counted 4.
Yeah, shame on you, the other guys. A Compost Shader lets you combine 2 different shaders. So if you want to draw a gradient, that's a shader. If you want to texture something, you use a shader, and you can compose them in one operation. So the limitations we have is that you can't recursively use compost shaders, and the 2 shaders inside the compost shader have to be of different types. So you can't use 2 bitmap shaders at the same time or 2 linear gradient shaders. And the workaround for all these limitations, pretty easy if you have custom code that uses any of these APIs or that requires any of those limited functionalities, just use software layers on your view. And so we told you that you should not worry too much about the compatibility of your app with the rendering pipeline because obviously it works for very complex applications that we ship. But you have to be aware of the new drawing model. We had to make some changes to the rendering model that exposed bugs in applications. Those bugs were actual bugs, but that did not show up as bugs on screen. So Chet will take you through the old rendering model and the new rendering model, and you will understand what you should do and what you should not do in your app.
So in the old rendering model, if a view changed, so let's say you changed the text on a button, then internally we're going to invalidate that view and tell the system that it needs to be redrawn. If it's a custom view, some property changes and you call invalidate on the view yourself. Same model. So the view gets invalidated, and it propagates that information up the tree. It says, okay, parent, I need to be invalidated. You need to invalidate yourself. And it walks all the way up the tree to the view root. And the view root says, okay, things are invalid. They need to be redrawn. So I'm going to tell the children need to be redrawn to draw themselves. So we're going to tell the parent to redraw itself, and then the parent redraws its children. And everything is very happy. Now, the thing that we did to make some of the GPU stuff more efficient was basically to not redraw anything that hasn't changed. So we created this thing that we call display list, which is basically a cache of the rendering operations that are going to happen for a particular view. So there's no logic in this thing. It's just the rendering operations themselves. For a button, there's going to be drawing a border, or filling the background, drawing the text, whatever it is. Right? So for instance, we can take a look at the code. This is actually output from a logcat when we've got a debug mode where we can actually see what the display lists are to help chase some issues down. So we're saving a context. Then we're drawing the patch that the button is using. We're saving the context again because we're about to change some transform information. We have a clip rect. We translate to get to the interior because we're about to draw the label itself of the button. And then we restore the context that were saved. So this is basically the way all of our display lists look, is this list of commands for any particular view. And then if it's a parent, it's going to be a list of its drawing commands, and then all of the stuff that's references to the display list inside the parent of the children. So the new rendering model looks like this. You invalidate a view. Something in the view changes. You invalidate it. That marks its display list dirty. Now, one of the things to note here is the parallel nature of this thing. So for every view, we have a matching display list. So every view knows how to draw itself with its display list. So the view gets invalidated. It marks its display list dirty, which means my display list needs to be recreated. It invalidates its parent. Now, notice the parent didn't actually get dimmed out here because the parent does not need to be redrawn. The parent simply needs to redraw its children, which have changed. Right? So we're basically propagating the information up the tree to say something in the tree has been invalidated and it needs its display list recreated. So the view root gets this information and says, OK, tree, recreate the display lists that need to be recreated. That does not recreate the display list at the top for the view group. It just recreates the display list for the child that got invalidated. And then it tells everybody to draw, and that basically issues the display lists again, which is a very quick operation compared to actually redrawing everything. So notice the view group didn't get redrawn here. Instead, the view group just issued its display list and the display list of the children. The only thing that got redrawn was the actual view that got invalidated.
And to better understand why this is so important, we're going to look at a simple example. So here, this is the settings application running on Android 3.0. And we're going to just click on the Wi-Fi setting list item. And when we click on this item, it turns blue. So now I'm going to show you a simplified version of what happened before Android 3.0. So just to turn that item blue, we had to redraw everything that intersected with the list item. That means that we have to draw the background. So there's a background texture in the back of the window. We had to redraw the panel. There's a gray panel behind the list. Then we had to redraw the text selector. We had to redraw the text on top of the list item. And then we had to redraw the checkbox on the right. And that is a lot of code to run. If you look at the source code of the Android platform and you go look at what's in the drawing methods of list view, of text view, you will see there's a lot of logic. It's not just simple, a canvas.drawLine. There's a lot of information there. With the new model, what we're able to do is run only the drawing method for the selector, because only the selector turned blue, and then we can just call draw on the display list themselves. So we run a lot less code at the Dalvik level, and then we can just run this very simplified native list of drawing commands in native code very fast. So this is very important. With the old model, if you called invalidate on a view, that view will redraw. But if you called invalidate on a view that intersects with another view, that other view would also redraw. And I've seen applications, we run into this issue internally in some of our applications. Our developers turned on the hardware acceleration, and suddenly they had views that would not redraw because they were relying on the fact that by redrawing another view, a second view would draw as well. With the new system, we will only redraw views on which you call invalidate. And that was always the contract. The framework should only redraw views on which you call invalidate. There was just this weird side effect that made it work in that special case here. So if you turn on hardware acceleration in your application and you have views that suddenly don't refresh, make sure you call invalidate on any view that requires it. And most of the time, you don't have to worry about it. If you change a view property, like the background drawable, the text, the framework will do it for you. So most of the time, this issue arises in custom views.
So an important case of this is worth understanding more. It's not just views that intersect, it's also the parents that gets in the way here. It used to be the case that if you invalidated a parent, your child would get redrawn. So if your custom view changed, you could invalidate the container that it was in, and everything would get redrawn, and life would be good. In the new GPU model, we do not redraw that view because we haven't been told that it changed. We will redraw the parent, and then the parent will reissue the display list for the children. So we can visualize this by saying, OK, we invalidate the view group. That gets dimmed out because it's going to be recreated here. That invalidates all the way up. The view of root says, OK, redraw yourself, and the view group happily does that. Actually, this is the old model, right? So it's actually going to redraw the children. And life was good. Oh, I wanted to redraw that view anyway, so the correct thing happened. However, in the new model, we now have these display lists. We invalidate the view group. It marks its own display list dirty and invalidates all the way up, so the view root knows what to do next. And it says, OK, redraw yourself. And the view group happily rebuilds its display list. And that's it, right? It did not actually rebuild the display list of its children, which means if one of those children changed, we haven't done anything to update the display of it because we weren't told that it changed. This is a very important element in getting the performance that we needed for the platform because we really don't want to do anything that we absolutely don't have to do. It's one of the ways that we get the performance that we do on these devices, right? So you need to be aware of that and construct your application accordingly. If you're using standard views, they do the right thing. They do invalidation internally. You do not need to worry about that. And in general, you're probably doing the correct thing anyway. But if you notice that a custom view is not actually getting redrawn correctly, then you might examine this a little bit more closely.
So we mentioned before software layers to work around some of the limitations of the hardware pipeline, but we have another type of layer. So we want to talk about that because they're extremely useful. So there's a new API on Vue called setLayerType. You can specify the type. We have 3 different types. And you can also pass an optional paint, and we'll see what the paint is used for. But most of the time, you'll probably pass null. So even with the new model, so here we have the example of drawing a button. So the button has a display list, and the display list contains a series of drawing operations where we save the context, we draw a patch, we draw the text, and so on. But when we need to draw that display list, we still need to run a fair amount of code at the OpenGL renderer level to convert those calls into OpenGL code. And that can be a little bit too much when you are trying, for instance, to animate very complex views, like a list view. So with layers, you can think of layers as caches. With layers, what we're going to do is we're going to use that display list. We're going to render it inside this layer. This will be, for instance, an OpenGL texture. And then when we need to redraw the button on screen, if the button hasn't changed, if you haven't called invalidate on the button, and you're only moving it, we're simply going to draw the layer itself. So it's one operation. It's very fast to do on the GPU. And here are the 3 types of layers. We have the layer none. This is the default value. That means the view does not have a layer. We have the software layer that we talked about. So when you use a software layer, the view will be rendered into a bitmap. So it will use the old software rendering model to render the view inside the bitmap. The bitmap will then be converted into an OpenGL texture, and then we'll render that texture on screen.
That's basically equivalent to what?
Render
cache.
Yeah, there's an API called setDrawingCacheEnabled. It does the exact same thing. And now we also have the hardware layer. So the hardware layers are very interesting because we can use the GPU to render the view inside an OpenGL texture, and then we can render the OpenGL texture with the GPU. So it's extremely fast. It costs GPU memory, but it's something that we can afford. So the reason why you should use these different types of layers, we have several reasons. The first one is performance. So if you need performance, especially during animations, you should use hardware layers. And we'll see an example of how to use them properly. And to give you an idea of how useful the hardware layers can be, this is a small comparison of performance to draw a list view. So if we render a simple list view on Android 3.0 using software, it's going to take about 10 milliseconds, which is way too much to get nice, smooth frame rate. If we use display list and the GPU, it takes only 2 milliseconds. But that's still a fair amount of time if you're moving other complex views on screen at the same time. And if we turn that list view into a hardware layer, it takes only a fraction of a millisecond to do it. So it's extremely efficient.
I like it. It's like a factor of 1,000 speed up by using a hardware layer. That's pretty cool.
Software layers and hardware layers can be used for visual effects. I mentioned before the optional paint that you can pass to the layer type API. And it can be used to control how you blend, how you composite the layer on screen. So you can use it to apply color filters, for instance. You can also apply transparency, and you can change the blending mode. So here, I have a screenshot of a modified version of the launcher. So I modified the launcher to apply one of those special color filters onto hardware layers. When you go into the all apps list in the launcher, each page of your all apps is one hardware layer. So all I had to do was add a few lines of code to turn the page into a grayscale page.
This is the launcher that came out in the 1930s before they had color.
Yeah, now we can afford colors. So this is the code I added. First, we create a simple color matrix. We set the saturation to 0. Then we create a new paint. We set that color matrix as a color filter. And then when we enable the hardware layer, we just pass that paint, which means when you draw that layer, please set the saturation to 0. And that's all you have to do. Layers are also useful for compatibility reasons. We mentioned it before, just use software layers if you rely on stuff that we do not support. And animations, if you use hardware layers and software layers, you can get really good performance when animating. And Chet will tell you a little bit more about that.
So one of the things that we did in 3.0 was to add a bunch of properties to Vue. This was as part of the work that I was doing on the animation framework. The way that you used to change properties like the translucency of a view was by using an alpha animation, which was nice if you wanted to actually fade in or fade out, but if you actually wanted the view to just be translucent, there was really no way to do that without a really sort of hacky workaround of using an animation as a side effect. So we've actually put properties on views where, frankly, they belong. So there's some very simple properties that affect the way that a view is displayed. There is the alpha property that affects the translucency. There's some post-layout translation properties, so you can move the view around within the layout after the layout positions it. You can scale it, you can rotate it, including rotating it around the Y and X axis for 3D rotation. And finally, you can declare the pivot point around which scaling and rotation happen. So all of these properties share the common attribute that they are actually set by the parent prior to drawing the view. Now, the nuance there that's important for animations and layers is that that means that the view itself is not changing, only the display attributes of the view that are handled by the parent change, which means that if you draw your view to a layer and then change the attribute, well, that layer can simply be copied after the parent sets the attribute. So we can visualize this a little bit here. So if you set the rotation Y property, for instance, you're going to rotate by 45 degrees around the Y-axis. That invalidates the parent. Note that it didn't invalidate the view itself. The view knows that this is one of those properties, these magical properties that are actually handled at the parent level. So it says, hey, parent, you need to be invalidated and you need to recreate your display list and reissue your children's display list. So the view group marks its own display list as dirty, and it gets recreated. And everything happens. It's all good. So we can see the code that actually happens at the display list level here. The original display list was the view group drawing itself, and then drawing the display list for A, and then drawing B's layer. So if you set rotation Y, then it's going to reissue the display list, but before it does that, it's going to set the rotation property and then reissue the layer. And the key here is that we didn't need to recreate the display list, right? So this could be a really complicated view that you have drawn to a layer, and then whenever we need to redraw it, all we do is copy the layer, which is an incredibly fast operation on the GPU. And that's how we got the 3 orders of magnitude speed up on that list view example that we saw. So we could touch on animation a little bit. So this is, we're not really going to get into the animation framework here. There's articles and presentations about that you can check out otherwise. But this is a little bit of code that animates the rotation Y property using the new animation framework in 3.0. So what you want to do, especially for complex views, is set a hardware layer temporarily, right? Layers tend to be expensive because they are large objects, so only use them when you need them. And in general, probably use them temporarily during an animation.
They're also expensive because if you might be tempted to enable hardware layers all the time, but if you have a list view and you enable the hardware layer, and the user starts scrolling the list, on every frame of the scroll animation, we will redraw the list into the hardware layer, and then we will draw the hardware layer on screen. So we will be doing twice the amount of work.
Right. So what you want to do is to set the layer, enable the layer, and then run the animation. But there's a little bit more to it because then you want to disable the layer when you're done. So the way you do that in the new animation framework is by setting the hardware layer, declaring the animation. So if you can't read the animation code here, it's basically saying I'm going to create an animation on the view object. I'm going to animate the rotation Y property, and I'm going to animate it to the value of 180 degrees. We're going to add a listener to the animation so that we know when the animation is done. And then inside that listener, we're going to disable the layer. We're going to set the layer type to none when the animation finishes. And then we start the animation, we're done.
And so now we have a few tips and tricks that you should be aware of if you plan on using the new hardware accelerated pipeline. The general tips and tricks that you can also use when you're doing software rendering. So the first one is pretty obvious. Don't use too many views. The deeper your hierarchy is going to be, the harder it will be for the system to render your UI in a very efficient way. You can have really wide view hierarchies. As long as they're flat, it's OK. But if they're really deep, then it's going to be very costly. And again, it's also an issue when you're doing software rendering. It's even more of an issue when you're doing software rendering because we have to redraw every single level when we need to redraw like one of the views at the bottom of the tree. I gave a talk, I think, in 2009 at Google I/O. The presentation is available on YouTube. I explain how you can keep the number of views to a minimal amount. So you should refer to that talk and make sure that your application does not use too many views. Be very careful of set alpha. So set alpha is this new property that we've introduced in Android 3.0. It's really cool because you can change the translucency of your view. You can animate your view. You can fade it in, fade it out. The problem with set alpha is if the view is not backed by a layer, software layer or hardware layer, we'll have to draw the view twice. We're going to first render the view inside an OpenGL texture, and then we're going to render that texture with the alpha value that you gave us on screen. So that means that we're going to have to process twice the amount of pixels. We have really cool optimizations to minimize the amount of blending that we're going to do, but it will cost you twice the fill rate.
Reusing objects is a good idea in general anyway, especially if you're in an inner loop, and particularly if you're running an inner loop in an animation. The VM is really good at collecting garbage. However, it does take some effort, right? So if you're creating a little bit of garbage every time you're running the animation frame because your inner loop is creating a new object and then getting rid of it, eventually you're going to get a GC, and if that GC happens in the middle of the animation, it may be noticeable to the user. It'll just cause a little hiccup there. So that's just kind of a general tip anyway. But there's another subtlety here with the GPU acceleration that these objects, the paints and the bitmaps, may be expensive for us to create because we're doing stuff at the GPU level of recreating these textures, re-uploading the textures that you don't really want us to do all the time. So keep these objects around and reuse them as opposed to creating them new every time. A link to that is don't modify the bitmaps very often. Every time you modify a bitmap, even if it's just a little bit of the bitmap, we actually need to upload a texture. That tends to be an expensive operation with GPUs. So you may have not changed much on that bitmap, but we basically need to send the entire thing over to the GPU, which is expensive. So don't do it if you don't need to.
It's actually a problem we ran into, I believe it was in the web browser during the development of Android 3.0. We noticed that the frame rate was not what it was supposed to be. And so we were looking at the code inside WebView, and we were wondering, like, why is the web page so slow to render? Until we realized that the tabs at the bottom, at the top of the screen, were modifying a bitmap on every single frame. And we were spending actually most of our time just rendering the tab at the top, not the page. So that was an easy fix.
Actually, it's really cool to have bugs like that during a release, because then toward the end of the release, you can make a very simple fix and just up the performance tremendously. There was an awesome speed up that we had in the animation system because early on in the development of the animation framework, I put in an arbitrary value that basically said, okay, we're going to get 30 frames a second here. And then a couple months later, I'd forgotten that I'd put this thing in, and we're trying to figure out how come we can't get to 60 frames a second. Everything has been optimized. We tuned everything here, and then I saw my little value there, and I changed it, and I checked it in, and we got 2x the animation performance. It's really awesome.
And actually, I have one more little story like that. The Maps application tried hardware acceleration, and they were disappointed by the results. And we had this back and forth on the bug report, and we were wondering what was going on because it didn't make sense. I think it was taking like 300 milliseconds to draw one frame. Until I finally used TraceView, which is an awesome tool in the SDK. And I realized that on every frame, when you scroll the map, they were reloading their XML, their menu from XML 96 times. So that took a little bit of time, and it had nothing to do with drawing. So, and that happens so many times, like very often, like the kind of performance bugs that we have, like use TraceView and look at how much time you're spending drawing and how much time you're spending doing other stuff. You'll be really surprised by what's going on in applications. So you can't always blame the drawing.
Was it TraceView I used to trace down the memory thing too? Was that allocation tracker,
Yep.
also in the tool, very useful. If the element I was mentioning about animations, creating a little bit of garbage and eventually getting a GC, allocation tracker in the tool is, in DDMS, is very useful for figuring out what is actually being allocated on the fly, because it may not be obvious from looking at your code, but it is when you look at the output of the tool.
So similar to not modifying bitmaps too often, if you're drawing a path and you change the path all the time, if you remember the example of a path that we showed you at the beginning of the presentation, we have this texture mask. And to generate that texture mask, we have to upload a texture and we have to render the path inside the texture. So if you change the path on every frame, we'll have to regenerate the texture on every frame. And it will be the equivalent of modifying a bitmap on every frame. If your path is relatively small, it's going to be just fine. But be very careful if you have a really large path that's pretty much half the size of the screen or more. Avoid overdraw. This is extremely important with the GPU because I mean we all think that GPUs are these awesome things that can run the 3D games, but games are really well optimized to draw each pixel once if they can. It's much harder to do that with the UI where we have several layers and very often we have anti-aliasing and translucency, and so we have to draw each layer. There's nothing we can skip. So to give you an idea, on the current generation GPUs, you can render about 2.5 times the number of pixels on screen per frame and run at 60 frames per second. So if you draw a background image and you draw a second background image on top of it and you can't see the one that was behind, like you have a background texture and then you put a white rectangle on top of it, that's already 2 times the number of pixels on screen, and most of your fill rate is gone. And actually, that's one of the optimizations we did in some of our apps. We have a default background texture in Android 3.0, and some of the apps were just covering it, and they were losing a lot of frame rate just because they were not removing that background texture. We have some optimizations to take care of it. They cannot always be applied, so make sure that you draw only what you have to draw. And finally, we just told you a few stories. If there's one thing you should take away from this presentation is profile your application. We have tools in the SDK. We have DDMS and TraceView. Use them. They will give you a lot of really cool information about what's going on in your app. And very often you might be surprised by what's going on. It's not necessarily your fault. Sometimes it's, you're calling an API and you don't realize that this very simple API, this one line of code, is going to do something very expensive. So if you have any doubt about the performance of your application, run TraceView, run DDMS, and go to the talk this afternoon about the tools. That's about it for today. If you want more information, there's an article that recaps all of this on d.android.com, the official development website for Android. We also post technical articles from time to time on our personal blogs. And we have time for Q&A, so if you have questions, please come to the mics.
And that's the end of the main talk anyway.
Yep. So quick question. So in the hardware acceleration thing, you generate shaders. Have you found any benefit compiling those shaders for the individual GPUs?
Compiling them too?
Compiling them. For example, I know PowerVR offers a GLSL compiler. Have you found any benefit there, or is it just good enough to hand it off to the driver?
I mean, the driver will do the compilation. We thought about caching the results. The problem is caching the result of a shader compilation is a proprietary extension. And for instance, the one that NVIDIA offers has severe limitations. Like it contains the current blend mode. So we decided against it because it was too complicated and didn't offer any real benefit for us.
So are you talking about caching the result from the on-device compilation, or actually compiling
From the
it?
on-device compilation.
Okay.
We can't afford to do, we're going to run on so many devices that we can't do the compilation
Sure.
ahead of time.
I just didn't know if
Yeah,
you
sure,
were.
no.
Yeah. And another question, Romain, what's your score on Stack Overflow?
My score, I don't know. We can look if
He
you want.
cheats anyway. He totally votes up his own answer.
Well,
see you later.
I don't know how you get any work done. I mean, every time I Google an Android problem, it's honestly like that. I might as well just Google problem plus Romain. So, anyways,
I just don't sleep very much.
okay, fair enough.
Hi. Do you know with 3.0, is it possible to get hardware acceleration of the HTML5 canvas element in the browser when drawing to it?
No, it does. It's one of the few things that it doesn't do, but I know that the browser team has plans for that.
Okay.
And our Q&A is going to be cut short because we were very late in starting, so we'll probably go a couple more minutes here, and we're going to be in and out of office hours, which is across the hall and upstairs.
So one thing I noticed while using fragments is when you add fragments, or say if you're replacing fragments in Honeycomb, the animation is just terrible. It stutters a lot, and it kind of tries to hide one of the fragments, and it kind of readjusts the size and starts to show the other fragment, and it's really slow. I mean, why is that? I mean, and I'm not using any custom animations on fragments.
That sounds weird because we use fragments in the standard applications and we don't have these issues. So that's why you should profile. So profile the application and try to see where the time is spent. And then you can probably do stuff like enable hardware layers or try to reduce the number of views you have to improve the performance. I mean, it's great to run on the GPU, but GPUs have their limitations. If you give us too much work to do, we'll happily send it to the GPU, but it's going to choke on it.
It could be that the fragment is doing something like, the animation that's happening is resizing the fragment, and if you have a really complex layout, well, resizing is going to cause a layout on every frame.
I don't have a very complex layout. There's a simple list, which I mean, and even the list items itself is just like probably just text or two lines of two text labels.
Have you turned on hardware acceleration?
Yes, of course.
Okay. Then profile the application, see what's going on, and file bugs if it's our fault.
And the other question I had is, I mean, why do you need to turn on hardware acceleration? Why can't the system be smart enough
that's
to kind
pretty
of
obvious.
do that?
We showed the limitations. Like we can't guarantee 100% compatibility with the apps. So if you have an app on market and we turn on hardware acceleration for you, but it makes your app crash, then your users won't be very happy with you, and it's going to be our fault. So we don't want that to happen.
Shouldn't it be transparent to the user if a hardware acceleration is turned on or off?
It can't be transparent to the user if we don't support something that the application depends on, and we don't know that the application depends on it, right? So we could either opt in everybody by default and end up really messing up some applications that weren't doing anything wrong to begin with,
right?
Or we could have you choose to opt in after you test your applications, which is probably a more robust model.
But our goal is somehow, someday to make it a default.
Yeah, because I've seen that there are lots of flags.
Sorry,
that
if you can catch us later, we can't debug it anymore from there. But we'll take one more question, and then we should shut this down.
Yeah, sorry, I apologize if this was covered, but was there any enhancements that would benefit apps that still have to target older platforms? Like 1.6 and up, let's say.
So yeah, if you target an older platform, you will have to do some trickery to enable hardware acceleration, but that's doable. And if we constantly optimize the framework, so if you don't use the hardware acceleration, we try to make the software pipeline faster. I can't give you any number, but.
So I would be able to add the line in the manifest, and that still would work. And then
yes, if you target, if you change your target SDK to 11, you can add the attribute, or you can do it from code. You can have a special case like if you're running on Honeycomb, then you can run that line of code.
Okay, thanks.
And that's it. Thank you.